All right, welcome back. So now we're going to continue and we're going to use our evolution equations to preserve the curvature condition. So you remember we had this condition, uh, we had a condition on, I'll draw the functional here, L times the curvature in L2 and ds. Okay, and so we assumed that this was smaller than a number, so 2 pi over 9 for the curved diffusion flow, or just pi for the free elastic flow. And we would like that assumption at time 0 to be preserved, so to continue to hold for all the curves along the flow. So let's call this preserving abound on that. Okay, now I'm going to have to give you a little warning. We're going to amp up kind of the level of the shortcuts that I'm taking. So I'm going to be using a few things. Now you can take them as black boxes if you're new, but if you have some experience or if you want to dive deeper into why these things are true, I'm going to give you a few pointers. So let me make my little pen red. So this is sort of a warning, not a warning, just a caution, whatever. You can still watch what I'm doing and you'll still get the basic idea. It's just that you will be, some steps may be like, what's going on? So things that I'm going to be using are, well, of course, integration by parts and so on. I will be using that a lot, but simple integral estimates. I'll tell you when it happens. So these will be things like the Poincare inequality. Now we're only talking about curves here, so it's just one-dimensional. So it's not too difficult, but it is a little bit. There are a few different versions of it, and we're going to be using the L infinity and the L2 versions, and Wirtinger. So Poincare and Wirtinger. These are inequalities that relate the value of a function to the value of its derivative. So Poincare works when the average of a function is 0, and Wirtinger works when there are 2 points where the function vanishes. Okay, so in our case, this Wirtinger is going to be useful when you're talking about the derivative of curvature because of the no flux condition. It vanishes on the boundary. Whereas when you're talking about the curvature itself, you need to use Poincare because the integral of the curvature ds is the winding number, which vanishes. And that's automatically preserved along the flow, well, as we saw in the previous video. Okay, so this is the main thing that I'm going to be using. When I say pi Poincare, then I mean this. The other thing is that I'm going to have, at certain times, repetitions of existing techniques. And when I do that, I'll leave it as an exercise for the interested, enthusiastic, and energetic viewer. So feel free to have a go at those things. And if you need any more details, just let me know, or you can take a look in the research papers. Sometimes I'll be referring to sort of known methods and other things. I'll give pointers as I go, but that will happen a little bit more often. So I'll try to be explicit, but this is just a little warning. The second main thing is interpolation. And so this interpolation inequalities are again integral inequalities, and they are due to Gagliardo and Nirenberg, and then the ones that we're going to be using here are adaptations by Chuk, Kuvert, and Schätzler. And actually, I'm not going to even do that in detail. What I'm going to do instead is show you the final statement of what you get. So if you want the details of that interpolation when it comes up, it will be to look in Chook, Kuvert, and Schätzler. That technique, that paper, is a seminal paper in the field. It's incredibly important, so I think that I will write down the authors' names. So Chook, Kuvert, and Schätzler. It's from 2001, Siam Journal of Mathematical Analysis, and it's an excellent paper to read to be introduced to these techniques as well. Okay. All right. So warning out of the way. 5 minutes of warning. Sorry about that. Now let's get down to business. So we're going to make a claim. Okay. So this is going to be for the free elastic flow. So say we have a solution to the free elastic flow, and suppose that that solution initially has length and L2 norm of curvature below some number k, which is also below pi, then for all time, that is true. And now that's exactly what we want to prove. That's our claim. And I'll make some remarks, and then I'll do the proof. All right. So the first remark that I would make is that this term is the elastic energy, or it's 2 times the elastic energy, and it's monotone decreasing along the free elastic flow. So we don't need to worry much about it. This term is decreasing. What we do need to worry about is this term. And in general, circles, for example, under the free elastic flow, inflate. So we are worried about length. Length is something that we are worried about along the free elastic flow. So the main difficulty with this claim is to try and show that either something very strong, like the length is decreasing, or that their product is decreasing. Now, the method that we're going to use is going to show that the length is decreasing by itself. So this is kind of a cheat, because it would be much better if we could play off, Peter against Paul. We could make use the fact that the curvature is decreasing to control the product. Unfortunately, we can't do that in any way that gives you a better result than this. But of course, if you have ideas, go for it. All right, here we go, proof. So let me show you how that works. So like I said a second ago, we're going to be looking mostly at the length. So length prime, we've already calculated this. We calculated it maybe 2 videos ago. It's the integral of k times f ds. Now here in this case, the f is free elastic flow, so it's kss plus a half k cubed ds. And the first thing we should do, the first reaction, is always to integrate by parts. The boundary terms vanish because of the no flux boundary condition. Okay, and then this next term, this cube, combines with the single power to make a 4th power, and we get this term here. And then what do you do? Well, we estimate. We estimate 2 powers of k out the front in their supremum. Now this is a very crude estimate, but it's enough for us. Okay, so this is plus 1/2, and then we take 2 powers of k out in their supremum, or essential supremum, whatever, and we're left with this. And now we use the Poincare inequality to control this L infinity norm by the L2 norm of the derivative, which is a good idea because that term is exactly right there. Okay, so we've got ks22, and I'll just collect this at the front as a coefficient. This is going to be our smallness. This is going to be this term, this lk in L2 squared. Okay, and now the coefficient is very important that you get from the Poincare inequality in this setting. So if you want to see the details of this, I think it's in my paper with Valentina. The coefficient is 2L over pi. Okay, and then you're left with KS 2, just like that. Okay, and now, so we just collect these terms together as a coefficient. I'd keep a minus sign at the front, why not? 1 minus, you see these 2's cancel, and you're left with L K in L2 over pi. Okay, and now because this has been assumed, so this is assumed to be less than pi at, or less than or equal to pi at time 0. So at time 0, this length cannot increase. And the curvature term is decreasing, strictly unless it's a stationary solution. So that means that this carries through to all times, and the product is a product of something which does not increase and something which is definitely also not increasing. So their product cannot increase. So this means this remains bounded by its initial value. By k, whatever that number might be, as long as it was smaller than pi. Okay, cool. So that was our main job for the preservation of the bound for the free elastic flow. How does it change for curved diffusion? Is it really very different? Well, yes. It is a bit different because for curved diffusion flow, the curvature quantity is not automatically decreasing or non-increasing. It's not so nice. Okay, so we have to do something slightly different. Let's make again a claim. By the way, you can see that this assumption on the this quantity, this total turning quantity of pi, this is actually the main part where this assumption comes in. So it would be, remember that our kind of goal would be to show pi squared. So if this argument could be improved to make this pi squared, then there'd be a real hope of bridging that gap up to pi squared. That would be really interesting. Okay, so the claim here for curved diffusion flow now is similar, but we say if L times K in L2 squared is smaller than 2 pi over 3, then it remains true. Okay, so we also need it small. Okay. Sorry. Okay, and then it remains smaller than that value, whatever that might have been. Oops. Oh, man. At t, you know, for all t, smaller than or equal to k. Okay, so let's just say for all t. Okay, so now we need to do something slightly different because the curvature quantity is not decreasing automatically. Okay, so what do we do? Well, first we need to, so the way this proof is going to work is we want to calculate the derivative of these two as a product. We're going to try to deal with them together. And I'm going to take I'm going to take a shortcut, so exercise for the interested viewer. All the methods have been discussed already, integration by parts and the commutator, evolution equations, and so on will give you this formula. So we calculate that ddt of 3L K L2 squared. Okay, so you get a few terms after, and you're just integrating by parts here, so there's nothing tricky or serious going on. The first one is just what you get from the evolution of the length. For curve diffusion, it's a very nice term. Oh, so for curve diffusion, the length is decreasing automatically. I didn't mention that, but you know, we've got the opposite situation. Free elastic, curvature decreasing automatically. Curve diffusion, length decreasing automatically. They're not the same, but there's a certain, and they're not in, there's a sense of duality there, but they're not really dual to each other. But anyway, there's a certain kind of relationship between them. Let's just say it like that. Okay, move that across a little bit. And then there's the diffusion term that you get from integrating by parts on the highest order derivative. So you get two derivatives here. And then there's this reaction term. So there's a source term. You have to remember that the behavior of the curve diffusion flow is quite strange. It's very different in many different situations. And so this evolution equation is fairly general, and it will hold for curves that are closed, as well as solutions to this boundary value problem. So it's expected that we will not be able to get any sort of deep general result for the parallel lines case unless we use specifically that we are in that situation, which is basically the role of this assumption, by the way, because for a closed curve, this assumption cannot be satisfied, which is something that you can take as an exercise to prove for yourself. It's not super easy, but it's not super hard. Okay, so this is your reaction term. So we want to control this reaction term, and that's what we do. Okay, so we look at this guy, 3L, and then this is just the integral of k squared times ks squared. Okay, now what is this bounded by? We're going to use a similar thing as before, but now instead of taking out the k in L2 in L infinity, we're going to take the ks out in L infinity. So we go 3L, and I'll just keep this as a coefficient because this is going to be our, our quantity. Ks L infinity squared. Okay, and now we'd use the Wirtinger inequality instead of the Poincare inequality because we don't have that. Ks does not have zero average. Ks does not have zero average, but it does vanish on the boundaries, so that's important. So we get 3L, and so you actually have a different constant when you're using the Wirtinger inequality in this setting. Instead of 2L over pi, it's L over pi. At least for the L infinity version. For the L2 version, they actually have the same constant, which is interesting. It's in the paper if you want to have a look at it. So you get KSS in L2 squared. And then just look at this coefficient. If you look at this coefficient, you've got 3L squared over pi times your k in L2 squared, and over here you've got 2L. So what we want, okay, so let me just write this down. I'm going to ignore this term in the middle here. So we've got, actually let's just, to make this super clear, let's make a little substitution. I'm going to use this character phi for the quantity that we're trying to control. Okay, so this is the quantity we're trying to control. And we've got ddt of this phi smaller than or equal and minus. Okay, now I'm going to take an L out as a common factor because it is a common factor. And then we've got 2 from this term here. Oh, you can't hardly see my cursor, but well, hopefully you can see a little dot moving around. So 2 from this term here, that's what I mean. And then you've got 3 times the quantity over pi here. So let's go 3 over pi times the quantity, like that. And then you just have a positive factor, which happens to be this. Just like that. Now, what does this mean? It means that if this coefficient is positive, then this quantity decreases, which is actually the claim, right? Because if phi is 2 pi over 3, then this is positive. It's not negative, at least. And that is how that works for curved diffusion flow. Okay. That is all I wanted to get through for this video. Next time, so what we've done is something really big. We've preserved our total turning condition. So we've shown that if we start off with this condition, then it's preserved for future curves along that flow. Now, what we have not done is show that the flow actually exists forever. That's going to happen next time. And you might think that will take a lot of work, but I'm going to lean heavily on Chook, Kuvert, and Schätzler. That's what we're going to be leaning on to get infinite time existence. So the next video is going to be more big picture, less calculation, and then after that we'll get back into calculations. Okay, I'll see you then. All right, thank you for your attention. Peace.